Hello everyone, I am Alok Kumar and I welcome you to this fourth lecture on matrices and determinants. We have already covered a lot of theory and today I propose to start with Cayley-Hamilton theorem, which is really beautiful for its applications, and we'll also cover many more things. So let me now quickly share my screen with you all and start the lecture. Okay, so as I promised you that we will first begin with something called Cayley-Hamilton theorem. So let me write that what it means and why it is important. So there is a theorem that goes by the name of Cayley-Hamilton theorem. Two people. Although explicitly it is not mentioned in J advanced syllabus, but still it gets to see lots of applications. So we would do well to cover it. Let me prepare some background for it. We already know what we mean by polynomial. So let f of x is ad x to the power d plus a d minus 1 x to the power d minus 1 and so on till a1x and plus a naught. This is your usual polynomial. So it's a polynomial. Let me call it ordinary polynomial. So this is an ordinary polynomial, means you're in algebra in variable x. Now we can also define something called polynomial functions of matrices. So we can define polynomial functions of matrices. What we do is that we replace x with a and we replace 1 with I. That is in the law, that is a naught gets replaced with a naught I. For example, if you have f of x is x squared minus 5x plus 6, then we can have f of a as a squared minus 5a plus 6i. This I is introduced now because anyway, suppose I had written a squared minus 5a plus 6, it would be meaningless. You can't really add apples and oranges. There is no meaning for a plus 6. It's meaningless because operation plus can combine two matrices or two numbers, as the case may be. There is nothing like it will combine one number and a matrix. So whenever the last term is there, I will write I, 6i. So given a polynomial, I can define f of a as this much, a squared minus 5a plus 6. So I will call it a polynomial function of matrices. So it's a polynomial function of matrix A. For the general case, f of x that I have written here, I can define f of a as ad and a to the power d and a d minus 1, a to the power d minus 1, a1a, and be careful in the last term, I will have to write a naught I. This is important, a naught I. Of course, nobody would forget that once they have been told clearly, but for the beginner, it looks somewhat amazing. So it's a naught I. Now, the moment we have defined like this, we know that fx is factorable as x minus 2 and times x minus 3. That's factorable. Similarly, you have this fa also factorizable, and we can write a minus 2i. So this 2 just gets replaced with I and a minus 3i. What is more is that one can also write as a minus 3i times a minus 2i. That is, they commute. We know that a minus lambda I and a minus mu I, we have done before, that they commute. Because scalars commute, and of course this is only one variable, a is there are no two matrices. So we don't have to worry about that. So having defined this, now we say that what the rule are there for governing this. So if we have f of x plus g of x, so if f of x plus g of x is h of x, if we have things like this h of x, and fx times gx is nothing but q of a, q of x, some polynomial. Then if you do it for matrices, then f of a plus g of a still is h of a, and f of a times g of a is still q of a. Means you can replace x as if x is a matrix A. So this is what is known as the algebra of polynomial matrices. Now this happens because scalars commute with each other. So we know that scalars commute, and also that distributive and associative laws, they hold. So our thing is fine. And last thing could be that exponent laws for numbers work as they work for matrices. Of course, for example, a to the power 4 and a to the power 5, you multiply matrix, you get to the power 9. Number also x to the power 4, x to the power 5, you get x to the power 9. So that tells you that we can do this sort of thing. Now we come to a statement of the theorem. So let A be a matrix Aij, that is n by n matrix, that's n road square matrix. So n road square matrix, that's n by n. And you want to evaluate the matrix A minus lambda I. We have defined some matrix A minus lambda I, lambda being a scalar. That is, if A were A11, A12, A1n, and let us write a couple more things, 211, 22, and 2n, in the last row will go an1, an2, ann. If this is the matrix A, then A minus lambda I, this is a new matrix in which the elements in the diagonal get subtracted by lambda. So A11 minus lambda, A22 minus lambda, all the way ann minus lambda. Others stay put, other remain same, A12, A1n, and similarly A21 and A2n, and this an1 and an2 and all those numbers. Now the determinant of A minus lambda I, that is, if I write det of A minus lambda I, so this sign goes off and determinant sign comes, is the same matrix A11 minus lambda and A22 minus lambda and an minus lambda, and all those A12, A1n, A21, A2n, an1, A12, and this kind of thing. So this is the determinant, and now we know it's a polynomial in lambda of degree n, because A has got n by n is dimension. So this is a polynomial. So this is a polynomial of degree n in lambda. Lambda is the variable. So this determinant is called the characteristic polynomial. This is called the characteristic polynomial of matrix A. Means it's a polynomial in lambda, and we name it as characteristic polynomial of matrix A. So if you expand it, we'll get something like det of A minus lambda I equals minus 1 to the power n and lambda to the power n, and plus A1 lambda n minus 1 and all those numbers. We don't care about A1, A2, A1, they're just coefficients. So once we get that, then this is your determinant, and this is a polynomial in lambda. If I write det of A minus lambda I equal to 0, then this will give an equation. I will call it characteristic equation of matrix A. This, of course, is a polynomial in lambda. Now this is how the theorem gets its name from now. So the theorem says now, the theorem name is Cayley-Hamilton theorem, and the theorem says that every square matrix that is n by n, every square matrix satisfies its characteristic equation. That is, if lambda n plus a1 lambda n minus 1 and all those numbers n equal to 0, it's the characteristic equation. Then matrix A satisfies it, that is A satisfies, that is a to the power n plus a1 a to the power n minus 1 all the way an times I, don't forget this I, as I've been cautioning you, equal to 0. This is a matrix equation. And so if somewhere to plug the values of A, he will find exactly this whole thing goes to 0. So that is meaning by saying that every matrix satisfies its characteristic equation. Let me take an example which will make it more clear. So suppose you have got a matrix A 2 by 2 for simplicity. So 3, 1 and negative 1, 2, this matrix. Then I can find its characteristic equation. I can find A minus lambda I. So A minus lambda I determinant that I can write as 3 minus lambda, 2 minus lambda, 1 and negative 1. And that equals 3 minus lambda times 2 minus lambda and plus 1, which can give you lambda squared minus 5 lambda plus 6 plus 1. That is lambda squared minus 5 lambda plus 7. So we have got the characteristic polynomial. You have got the characteristic polynomial as lambda squared minus 5 lambda plus 7 is 0. Now every matrix A satisfies its characteristic equation, meaning that you can replace lambda with A and it still holds true. Means A squared minus 5 times A and plus 7 times again write I, otherwise there is no meaning, equals 0. That's what we mean, that we have got an equation but in polynomial such that A is a root of it or A satisfies it. This was in scalar algebra, ordinary polynomial. This is your matrix polynomial in which A is the matrix is involved. So A satisfies this. Now, because we know A satisfies this, we can check also. One can run a check. That's trivial. So let's assume that okay, A satisfies this because Cayley-Hamilton theorem says it. And now let me do some problem based on this. So for example, in this same question, I can ask you that express, or in objective format we can say it differently, but let's do this one. Express 2a to the power 5 minus 3a4 plus a square minus 4i as a linear polynomial in A. That is you want to find 2a5 minus 3a to the power 4 plus a to the 2 minus 4i is lambda a plus mu I. You want your ordered pair lambda mu, as Jay has asked a couple of times, this kind of thing. So you want to find this one. Now, had we not known this theorem, Cayley-Hamilton, we maybe had found some kind of a to the power 5 or larger powers, or we may have found some pattern. But Cayley-Hamilton theorem, a strong point is that to begin with, you get an equation in A. So already you know an equation. So you already know that A satisfies this much. So this question meaning is this, that okay, if you have got something like 2x5, so you want to express something like 2x5 minus 3x4 plus x square minus 4 as x square minus 5x plus 7 times some quotient and then some coefficient. So call it, because a symbol is used, so I'll avoid that symbol. So I can say that you want something like, you want px n plus q. Means you want that when you divide 2x to the power 5 minus 3x to the power 4 plus x square minus 4 by x square plus 7, then the remainder is px plus q. I want p and q. The moment I get p and q, I can write by virtue of this 2a to the power 5 minus 3a4 plus a squared minus again 4i, not simply 4, is a squared minus 5a plus 7i q a and plus pa plus q. Still they are numbers, and because this is 0, so I've been able to express this number as pa plus q, and my p and q only are my lambda and mu. So the question is just algebraic in nature, and that's your class maybe class 7 or 8 level problem, that divide 2x to the power 5 minus 3x4 plus x squared minus 4 by x squared minus 5 equals to 7 and tell me the remainder. So we will do by something called long division. So x squared minus 5x plus 7, we want to divide. So we want to divide 2x5 minus 3 squared 4 plus x squared minus 4 by this expression. So let's keep doing the long division and we would be fine. So first step would be that we will do, this is 2x cube. So you will have 2x cube, that is here 2x5 and then minus 10x4. So that's 10x4 and plus 14x cube, which is not here. So I'll write separately 14x cube as it's not here. Change the sign, negative, positive, negative. This goes away. Now we are left with 7x to the power 4 and arrange the order, minus 14x cube and plus x squared minus 4. Now 7 has come up. So I can write here plus 7x squared. So 7x to the power 4 minus 35x cube and plus 49x squared. And then again we can change the sign, negative, positive, negative, the way in doing division algorithm. And so we are getting here 21x cube minus 48x squared and plus 4. This negative 4 other. And then we will write here now 21. So 21x. That will give you 21x cube and minus 105x squared and 21 into 17. So that's not here. So 147x. So I can again change the sign. So negative, positive, negative. And I'll change the page and I can write 105 minus 4, 48. So that is your 57x squared. And in order, minus 147x and minus 4. And now 57 comes up. So now here we will have plus 57. And that will give you 57x squared. And 57 times this 5. And that number is minus 285x. And that other number, 57 into 7. So that is 399. I can change the sign again. Negative, positive, negative. So we are getting here 138x, and this is minus 403. So it means that we have got this remainder. So let me go back and show you that this is what we accomplished, that this part we have done, that we said that 2x to the power 5 minus 3x4 plus x minus 4 is x squared minus 5 plus 7 times qx, which of course we got the big one, but we don't care because ultimately this will go to 0. And px plus q. So we can write here now p and q. So our p and q is this much. So it means your p becomes 138 and q is minus 403. And that's what your lambda and mu are. Because when you put a, this term goes to 0. So you have been able to express this fifth degree polynomial in a as a linear polynomial in a. That sums up this quite beautifully. And we get this answer. We can also have a different method, but I would assume this is faster. Some people do like this, but then I don't recommend. I'll just write a few lines to tell you that please don't do this. Somebody can write a squared is 5 minus 7i, and then you can write a cube is 5a squared minus 7a. And again, you can write 5 and a squared is 5a minus 7i minus 7a. So it's right 25a and minus 35 and 7. So sometimes 42a. No, this is like 25a. So it's like 25a. And so 25a minus 35i and minus 7a. That is 18a minus 35i. And then similarly for a4 and a5, you can keep on doing. And you can plug these values in the end. That would be, of course, longer. It may be looking nice, but it is still longer. So just prefer the division algorithm. For those who know, we can also prefer, and we can also do, that's much more time saving, something called synthetic division. Just look it up. That's very simple. So if you are not familiar with this division, you can look it up. If you are familiar with it, then do use it. Otherwise, this always works. It is a little longer, maybe 30 seconds more than this one, but still both are okay. But this is not advisable that A square and writing powers. This works only in certain cases, not all cases. Okay. Next, let me do one problem that connects inverse with it, and then your polynomial, your degree of this polynomial also becomes 3 because matrix is over 3. So let the matrix A be given by 2, -1, -1, -1, 2, -1, and 1, -1, 2. That's your matrix A. Now, it is known that A inverse exists. The question only tells you. So you are being asked that if A inverse is alpha times A squared plus beta times A and plus gamma times I, then find alpha, beta, gamma, the ordered triple. So you want to find this ordered triples alpha, beta, gamma if the matrix satisfies something like this. So of course, we don't calculate A inverse directly. Rather, we fall back on Cayley-Hamilton theorem. And first of all, we say that, okay, the matrix A is given. That's 2, -1, 1, -1, 2, -1, 1, -1, 2. Let me find its characteristic polynomial. Let me find characteristic polynomial. That is det of A minus lambda I. And that is everywhere things are same. Just subtract lambda from each diagonal elements. So just write 2 minus lambda, 2 minus lambda, 2 minus lambda. They are all same, which need not be always true. And -1, 1, -1, -1, and 1, -1. This will be just copied as it is. Now your job is to evaluate it. I see over here 1 and -1 and other things. And maybe this also, -1. So I'm prompted to make this kind of thing that I will just change R3. So I would like to change R3 to R3 plus R2. So 2 minus lambda -1, 1 is step put, -1, 2 minus lambda -1. And then change R3 to R3 plus R2. So add R3 to R2, that is 0. 2 minus lambda -1, that gives 1 minus lambda. And that also gives you 1 minus lambda. They are same. They are just same in different order. So 1 minus lambda is not surprising. Take 1 minus lambda out from the third row. You are left with 2 minus lambda, -1, 1, -1, 2 minus lambda, -1, and 0, 1, 1. I love the ones over here because I know we can do something about it. So 1 minus lambda. And this time I propose that I would change, say, C2 to C2 minus C3. So I can write 2 minus lambda, -1, 0 copied. Column 1, no change. Column 2, of course, column 3 also is step out. Column 2 changes. So subtract 3 from 2. So that is -2. That is 2 minus lambda -1. That's 3 minus lambda. And this 1 minus 1 is 0. And now we are good. We can expand around the third row. And we are just left with this block. And that is 2 minus lambda, 3 minus lambda, and negate minus of 2. And that simplifies 1 minus lambda. It is lambda squared minus 5 lambda plus 6 minus 2, giving you 1 minus lambda in lambda squared minus 5 lambda in plus 4. And if you expand it as in lambda cube, so I'll get minus of lambda cube. That's all right. Lambda squared, I get 1 from here, lambda squared, and 1 from here, 5. So I get 6 lambda squared. Lambda, I get 1 minus 5 here, and here minus 4. So I get minus 9 lambda. And then I get just 4 plus 4. So I get this kind of characteristic polynomial in lambda. So if I turn it, I'll say that, okay, lambda cube minus 6 lambda squared plus 9 lambda minus 4 equal to 0 is the characteristic polynomial or characteristic equation of matrix A. Now we know that matrix A will satisfy it. A will satisfy it. That is known by Cayley-Hamilton theorem, satisfy it. And so it implies that A cube minus 6A squared plus 9A minus 4, don't forget the I, equals 0. And now we have ended up with a polynomial in A. We want A inverse. This constant term being not 0, this tells you that A inverse indeed exists. Otherwise, it won't be here. Infinity need to exist. And so I can write a cube minus 6a squared plus 9a. And I would like to write 4i on the left side. So 4i equals this. I can multiply with a inverse. So 4 times a inverse is a squared minus 6a. Power decreases by 1. And plus 9, this becomes I. And your a inverse is 1 over 4 in a squared minus 6a plus 9i, which I can write as 1 over 4a squared, 6 over 4a, and plus 9 over 4i. That is 1 over 4a squared minus this can give 3 over 2a, and plus this is 9 over 4i. So now my alpha, beta, and gamma, because we had a inverse was alpha a squared plus beta a plus gamma. Let's check it that this is what they said. Yes, alpha a squared plus beta a plus gamma I, that is a inverse. And you get a inverse this one alpha a squared. So you know now that the triples alpha, beta, gamma, they are just 1 over 4 and minus 3 over 2 and 9 over 4. So that's your answer. So these are the two good applications of Cayley-Hamilton theorem, and many more you can practice. It really helps a lot. So keep an eye out for it whenever you see a new problem. Let me now change track and then tell you something about determinants of adjoint. So adjoint, let me recall first what an adjoint is. So adjoint of a matrix, a useful concept that combines determinants and matrices both. So adjoint of a matrix, if you write, if you have got a matrix A is Aij, n by n square matrix, of course, then you can form a matrix which is called the cofactor of matrix of A. So I can say that let's take the matrix B defined by Aij capital A, Aij n by n, means this B is the matrix. B is the matrix formed by the elements of Aij with their cofactors taken. Cofactors taken means Aij, capital Aij, is cofactor of Aij. That's what we mean. That is the cofactor of Aij. So it's cofactor of Aij. And then if I take B transpose, then this only is defined at the adjoint. This is defined at the adjoint of matrix A. Adjoint of matrix A. Now, this has got many properties. The first property, that's of course the most important, I would say, that, and you must keep it in mind, that A times adjoint of A is adjoint A and times A. So let me put it also in bracket, adjoint A, and that is det of A times I. I have used it previously. So A adjoint A, that tells you that A and adjoint A commute. You know that not every two matrices commute. So it's good news. It's rather pleasing that A and adjoint A commute. So A and adjoint A commute, and you are finding the result that it's a scalar matrix that is the det A times I. Now, based on this, we can have some results which are important. So we'll do two small results. One is that if det of A, I will use symbol det. If det of A is 0, I can also use a symbol this like modulus. So both are same. If det of A is 0, then det of adjoint of A is also 0. So one has to prove that if det of A is 0, then det of adjoint A is also 0. Now, this question is really easy, but then we use it a lot. So I'll just say that, okay, that this can be accepted, and we will prove it. We'll prove the other results which are really important, and that is like this. That so one result says that A adjoint A, or this one, that, or let me first prove this so that you also feel that, okay, this is the kind of thing that we can do it. So this is when you say A adjoint A. So we're writing A adjoint A is determinant of A times I. And if you say the det of A is 0, det of A is 0, that gives you that A adjoint A equals 0. Now, what can we conclude from here? A adjoint A is 0. It's like PQ is 0. We have discussed this once. That PQ is 0 means what? So if PQ is 0 and there are no conditions on P and Q, you can't go further. So let's say that A adjoint A is 0, and let's make an assumption that whether A is a null matrix or A is not a null matrix. So if A is a null matrix, that is A is 0, A itself is 0, If A is 0, then obviously det of A is anyway 0 here. So if A is 0, then we know that adjoint A, also det of adjoint A will be 0, because adjoint A, there is no adjoint. So adjoint A is 0. So the really important case is if A is not a null matrix. If A is not a null matrix, that is A is not 0, then what we can say? Now come back here. PQ is 0 and P is not 0. What I can say about Q? I told you before that if P is not 0 and PQ is 0, means product of two matrices is 0 and one of them is non-zero, then the other, that is Q, then the other must be singular. Other must be singular. Q must be singular. Proof by contradiction. Just to refresh you, that suppose Q is not singular, means suppose det of Q is not 0, implies Q inverse exists, Q is invertible, exists, and so PQ equal to 0 gives me PQ post multiplied with Q inverse is 0 Q inverse, that is 0, and we get here P equal to 0. That's a contradiction because given P is not 0. So it means we have got A adjoint A is det of A times I, det of A is 0. If A is null matrix, nothing to prove. If A is not null matrix, not 0, then we know that det of other matrix adjoint A must be 0. So that is det of adjoint A must be 0. So we have proved in all cases that if det of A is 0, then det of adjoint A must be 0. So that's what we have done here. So let me use it to prove something else. So there is a result. It's also important, and it is really asked. Let A be n by n matrix. Let A n by n matrix. Then you want to prove that adjoint of A equals det of A to the power n minus 2 and A. Of course, n by n matrix, so we take n greater than or equal to 2, so that it's really a matrix. 1 by 1 means if it is 1 by 1, it's just a pure 2, this kind of thing. So we don't bother about this. So really matrix start with n greater than or equal to 2. So I take that adjoint A. Now, to prove it, we start again our fundamental identity that A times adjoint A times adjoint A is det of A times I. That's one thing. Because we have got adjoint of adjoint A, replace A with adjoint of A. That makes sense. So adjoint of A, and I write adjoint of A. So I'm using a lot of brackets, and this is det of adjoint of A, and then we can write that times I. This is what we can write. Now, if this is there, then let me start now this. So if adjoint A is there, so I can write here as adjoint A at C, or again pre-multiply with A. So I can write A adjoint A, and then adjoint A is A times determinant of adjoint A. That we already know. So det of adjoint A is known. That is like det of A to the power n minus 1. So we'll write this, that this is A, and this is simply this is a scalar det of A to the power n minus 1. So this is what we have got right now. Now A adjoint A adjoint A is again det of A and time this one. So A adjoint A, let's check again, det of A times I. So that gives you det of A times I. That I does not matter because I times this is still the same. So adjoint of A is A times det of A to the power n minus 1. And we can make the cases. So suppose A is not invertible, so then we can divide. So if A is not invertible, if A is, then of course det of A is 0, so we need not discuss that case. And if A is invertible, so this is one case. Other is if A is invertible. If A is invertible implies det of A is not 0, and then it's not trivial result. Det of A is not 0, so that then you can cancel det of from here, and you can get adjoint of A is det of A to the power n minus 2 and multiplied with A. So this is your result for this one, that okay, you are getting adjoint of A is det of A n minus 2 times A. Still we continue our journey with this one, and let's do another one, that A is n by n matrix, and you want to prove that det of now adjoint of A, so that equals det of A to the power n minus 1 whole squared. So this again we can prove by the thing we know already. So solution will look like that we have got already, we know det of adjoint of A is det of A to the power n minus 1. We just used the previous thing. This is true for any A. So let's replace A with adjoint of A. So we'll get det of adjoint of A. It's like bracket, adjoint of A is det of adjoint of A whole to the power n minus 1. Now, det of adjoint of A we just saw. So let me again show you the det of adjoint of A. We used here, det of adjoint of A is this much. We just used in this example here, det of adjoint of A is det of n minus 1. So I can write here as det of adjoint A. So this number, det of adjoint A, I can start from here, and I can write that this is nothing but det of adjoint of A. So adjoint of A is, so let me just rub it in colors. So this will give me that det of adjoint of A. So det of A to the power n minus 1, and this is n minus 1. And so you will get, this is nothing but det of A to the power n minus 1 whole squared. And that's our result, that det of adjoint of A is det of n minus 1 whole squared. These normally are useful when you have to calculate some adjoint, or maybe some relation some kind also may be asked. Let us do some problems on summing determinants, some values. So say we have got d of r is determinant is 2r minus 1, and choose r, first row 2 to the power r, second row goes like x cos square theta and y, and third row n squared 2 to the power n minus 1 and 2 to the power n plus 1 minus 2. And suppose I want to find sigma dr, r equal to 1 to n, lower limit is 1, upper limit is n. So I want to find this one. Now, for this we are using a result, a basic result, that if you have got a1, b1, c1, and say pqr xyg, and plus again a2, b2, c2, pqr xyg, and all sort of thing, a3, b3, c3. So two rows are constant, pqr xyg. Then we know that the determinant value that becomes, it's just a1 plus a2 plus a3, b1 plus b2 plus b3 all the way, and these pqr xyg are as it is. Means we can just sum along one row. So with this notation, with this thing, it becomes sigma dr r equal to 1 to n. That gives you that sigma transfers to the first row. So you are getting this as sigma 2r minus 1 r equal to 1 to n. Sigma n choose r. Notice r is 1 to n. And sigma, this is again a gp to the power r, but still r is 1 to n. And then you have got these x cos squared theta and y and n square to the power n minus 1 and to the power n plus 1 minus 2, that they don't depend on r. They are just independent of r. So summation is only on the first row. But now we know a result that sigma 2r minus 1 r equal to 1 to n. That is sum of first n odd number 1, 3, 5 and 2n minus 1. It's just n square. If you forget, you can derive also. They are first n numbers. So sum is n times their average of these first two terms, first last, 1 plus 2 minus 2 upon 2. And this gives you n square, just an AP. N choose r. If you go from r0 to n, it is to the power n. So obviously when you start at 1, so n choose r equal to 1 to n. So one term will be missing, so 1 minus 1. And similarly, this is gp 2 to the power r equal to 1 to n. That goes from 2 plus 2 square plus 2n. I can take a 2 out. 1 plus 2 plus 2 to the power n minus 1. And so 2 to the power n minus 1 upon 2 minus 1. So that you will get 2 to the power n plus 1 minus 2. And that's what you've got here. So it means using this, the first row rewrites as n square, and then 2 to the power n minus 1, 2 to the power n plus 1 minus 2. Never cared about the second row, that's here. And here n square, 2 to the power n minus 1, 2 to the power n plus 1 minus 2. So rows R1 and R3, they are identical. So these rows are identical. And so we know that once two rows or two columns are identical, then determinant value is 0. And so this determinant, this big looking determinant dr, this sum equals sigma dr r equal to 1 to n. This sum equals 0. So notice how we did not have to evaluate the determinant. We just had to find this thing and we were done. Now many questions also come on something called product of determinants. And it takes some care to find out that which are being multiplied. So that we will do one example to see that how it is coming. So we have got some determinant D is 2a1 b1 and a1 b2 plus a2 b1, a1 b3 plus a3 b1, and the second rows goes like a1 b2 plus a2 b1, 2 a2 b2 and a2 b3 plus a3 b1. And naturally third row, you have guessed by now that a1 b3 plus a3 b1. This is a3 b2 plus a2 b3 and twice a3 b3. And you want to evaluate D. Okay, so let me look at this determinant. And in fact, the first row first. And first row, I will write each element. For example, this element 2a1 b1, 2a1 b1. I want to write in this form. Means I want my boxes. I want it to write as a sum of three terms, and each term a product of two terms. So that this will go to I can change the color maybe, and then it will be good. So say I write this one this way and this kind of boxes, so that when I multiply the matrices, then I'll get these comes from the row and these comes from the column. Does it make sense? So what I mean is that 2a1 b1, I'll go back to the original color. So 2a1 b1 I want to write such that it is the sum of three terms, because we are doing 3 by 3 determinant, three terms, such that each term is a product of two terms, so that I can write this is green, so all this is here, this green boxes are here, this green ones, and the red ones are in the column. So we can multiply something called row by column. So a1 b1, 2a1 b1 I will write as something creative way. So I can write this as a1 b1 plus, so let me write this as a1 b1 plus b1 a1, and nothing is there, so I'll let 0 in times 0. Then a1 b2 I will write as a1 b2 plus b1 a2 plus 0 0. And the third thing I can write as, in the same manner, a1 b3 plus b1 a3 plus 0 times 0. Say this is a1 b1 and 0. Here also a1 b1 0, a1 b3 b1 0, and here you have got things b1 a1 0, that is changing now. So this is b1 a1 0, this is b1 a1 0, this is now say b2 b2 a2 0, and this is something like b3 a3 0. So you find that a1 b1 0 is all constant. So using this one, suppose I write my first row. So I'm writing this as a1 b1 0, and then if I define here b1 a1 0, b2 a2 0, and b3 a3 0, my matrix is getting filled up now. So first, only concentrate on first row, and first row will be obtained by multiplying first row of the left matrix with the 3 columns with the right. Means if you call this r1 r2 r3, this one, and you call this as c1 c2 c3, then first row means r1 c1 r1 c1 r1 c2 r1 c3. So my order must be same, so I chose a1 b1 0 a1 b1 0, and like this. Now we see the next one, that in fact the next one I can write as a2 b2 0 and a3 b3 0. Just check a couple of more terms. For example, here second row, a1 b2 plus a2 b1, I am getting a2 b1 plus a1 b2, that's fine. Then I'm getting a2 b2 plus b2 a2, that is twice a2 b2, and a2 b3 plus b2 a3, so that checks out. Similarly, third also checks out. And so I've been able to express the given determinant, the big one, as a product of two determinants, and in the form row by column. So multiplication row by column. You can also arrange row by row in determinant. Matrices you can't. So row by column multiplication you have done. And so we know that each of them is 0, effortlessly seen, 0 and 0. And so the result is 0, which was not very obvious for the original determinant. It was this. It was not obvious because we did not know that what value it will be. But it turns out it does not depend on a1, a2, a3, b1, b2, b3. That's quite amazing. Let's do a proof-based question of determinant. It asks you to prove that a minus alpha square, a minus beta square, a minus gamma square, lots of square, then b minus alpha square, b minus beta square, b minus gamma square, and c minus alpha square, c minus beta square, c minus gamma square, and that equals twice a minus b, b minus c, c minus a. It is cyclic order, and alpha minus beta, beta minus gamma, and gamma minus alpha. Looks quite big, the right side especially, but then we have some determinant form, because you see a, b, c, and alpha, beta, gamma are separated. So that tells you that it is something to do with product with determinants. So I can write my delta as, this is a square minus 2 alpha plus alpha square, a square minus 2a beta plus beta square, and a square minus 2a gamma plus gamma square. Similarly, I can write others also. So let's write one more term, b square minus 2b alpha plus alpha square, b square minus 2b beta plus beta square, and b square minus 2b gamma plus gamma square. And similarly for c. Let me again write this as some term in some other manner. So I can write a square times 1 plus minus 2a times alpha and plus 1 time alpha square. So if I write like this, they have got some pattern a square, this one. Then I have write again a square times 1 plus minus 2a times beta plus 1 times beta square, and so on for the last one also. Save for the last. Now my sign is coming up, so I can write here a square into 1 plus minus 2a times gamma and plus 1 time gamma squared. Now if I take my left matrix as a square minus 2a1, then I can fix these three columns, that is 1 alpha alpha square. See, a square minus 2a1, they all are same. Now 1 alpha alpha square, 1 beta beta square, and 1 gamma gamma square. What is left is just make b square and c square. So I can just write b square minus 2b1, c square minus 2c1. Now this 2 can be taken out and I can interchange them, the rows and the columns. So 2 times I can write 1 1 1 here, and then I can write ABC and a square b square c square. And then here 1 alpha alpha square is same, 1 beta beta square, and 1 gamma gamma square. The last step is to observe that you have got 1 x square, 1 y square, 1 g square. This determinant equals x minus y minus g minus x. One can of course get it by subtraction, or you can think of a polynomial in x. So suppose f of x is this much, f of x, then we know that x equal to y, then f of y becomes 0, and so x minus y is a factor. Similarly, f of g is 0, so x minus g is a factor. And other, you can say that symmetrically other also must come. So we use this twice, so twice into, I use it here, then I just get a minus b, b minus c, c minus a, and then alpha minus beta, beta minus gamma, gamma minus alpha. So that's what we will get directly by doing this one. Let's do one more, which is using the same result. So let me change the color and use something different. Now we have to prove that 1 bc plus ad, b squared c square plus a squared d squared, 1 ca plus bd, c square a square plus b squared d squared, 1 ab plus cd, and a square b square plus c square d square. You notice that how bc plus ad relates to b square c square plus a square d square. We observe that b square c square plus a square d square is bc plus ad whole square and minus 2 bcad, that is bc plus ad whole square minus 2 abcd. So if I write bc plus ad equal to x, ca plus bd equal to y, and ab plus cd equal to g, if I observe this, then my determinant delta rewrites as 1 1 1 x y g, b square, that is x square minus twice abcd, y square minus 2 abcd, and g square minus 2 abcd. So I can break it into determinants, that is 1 1 1 xyg, x square y square g square, and plus 1 1 1 xyg minus 2 abcd minus 2 abcd minus 2 abcd. I can take common negative in here. I can take that 1 1 1 xyz. I can take common negative of 2 ABCD. I will get here 1, 1, 1. These two rows become identical. Identical. It means that goes to 0. That's all. That goes to 0. So we are just left with this one, which we have seen is x minus y, y minus g, g minus x. You can always check the sign. This is diagonal is yz square, yz square. If you want to get yz square, you must get z from here, and y from here. So this is yz square. Now let's evaluate these things. So your x minus y is bc plus ad minus ca minus bd. I combine this and this and these two, so that means c times b minus a minus d times b minus a. That gives me c minus d times b minus a, which I can write negative of c minus d times a minus b. Let's get y minus g. So y minus g is ca plus bd minus ab minus cd. I combine this one and this one. A times c minus b minus d times c minus b, c minus b, a minus d. That is negative of b minus c, because I write order a minus d. And one more I will write g minus x. And so that is ab plus cd minus bc minus ad. Again, I can combine this one. That means b times a minus c and minus d times a minus c. That is b minus d, a minus c. That is usual order, b minus d minus c. So I will leave that order. It is same order. Now our answer is the product of all this. So that answer is the product of all this: x minus y, y minus g, g minus x. That becomes c minus d times a minus b, b minus c, a minus d, and times b minus d, a minus c. Now I can write in terms of the same thing as directly. So I can write a minus b and then a minus c, and then I can write a minus d. So we have a minus b, a minus c, a minus d. And also, once I get a minus b, a minus c minus d, come from b, we have got b minus c, b minus d, and then ultimately you've got here c minus d. So this determinant, we have proved that indeed the value is this one: a minus b, a minus c, a minus d, b minus c, b minus d, c minus d. So it turns out that we can use lot of things. So look for multiplication of determinant. Look for multiplication determinant. That is useful. And also that standard determinants, because you can evaluate them quite easily. So let me now stop sharing my screen. Okay, so that's all for today. Let us connect tomorrow again.